Welcome everybody and thank you for watching this presentation. My name is Darwish. I am doing my PhD in environmental engineering at Carleton University in Ottawa, Canada. Before I start, I would like to thank the organizing committee of this workshop and our sponsors, INSERC of Canada, Brookfield Global Integrated Solutions, and Capillary Analytics, and also my supervisors, Jean Decote and Borak Guney. In this presentation, I will talk about virtual metering of heat supplied by hydronic perimeter heaters in variable air volume zones. First, I will give a brief background, and then I will describe the research methodology, followed by the results and conclusion. The motivation behind this research was to provide a better understanding of how energy flows at the zone level and to provide virtual metering solution when physical meters are hard or expensive to install, and also to evaluate the performance of the modeling approaches that are used to create virtual meters. So the objective of this research is to examine the performance of 3 modeling approaches applied to develop virtual meters that would estimate the heat added by zone-level perimeter heaters. Now, submetering at the equipment level is essential to understand energy flows in commercial buildings, to optimize energy use, to detect energy use anomalies, and improve operating schedules. However, submetering of HVAC equipment is still uncommon in most existing buildings due to practical issues in the metering infrastructure. Moreover, physical meters are subjected to issues such as space limitation, improper installation, failure, and degradation over time. Virtual metering overcomes these issues by using available data from a building automation system and provide insights into unmeasured quantities at no additional cost. Now, the primary sources of heat gains and losses at a perimeter zone are internal heat gains from lights, occupants, and equipment, heat transfer through the envelope, heat added or extracted through the discharge air diffusers, solar heat gains, and heat added by radiant heaters. In this research, I wanted to develop a virtual metering algorithm to estimate the heat added by the radiant heater. It is uncommon to measure this heat despite its impact on the building energy consumption and operating schedules. The methodology of this research consists of 2 parts as shown here. In the first part, 3 modeling approaches are applied to formulate zone model structures: a steady-state modeling approach, a transient modeling approach, and a load disaggregation modeling approach. Now, datasets collected from 7 zones in an academic building in Ottawa are used to train the 3 models. The genetic algorithm is used to identify model parameters. In the second part, the values of the parameters are used to develop virtual meters that can estimate the heat added by the radiant heaters in the 7 zones. Now, the virtual meter results are verified by comparing the results to measurements collected from physical meters installed in the 7 zones. The performance of the 3 modeling approaches is evaluated based on the accuracy of the virtual meters. Now, this schematic shows the 7 perimeter zones in the academic building. These zones are served by 2 VAV terminal boxes, VB1 and VB2, that receive supply air from an air handling unit and discharge it into the zones through discharge air diffusers. These perimeter zones are provided with hydronic radiant heaters that use hot water and modulating valves to control the hot water flow rate. Now virtual meters are developed to estimate the heat added by the radiant heaters in these 7 zones by applying 3 inverse modeling approaches. First, a steady-state gray box modeling approach that assumes that energy is not stored within the zone. And the second approach is a transient gray box modeling approach that accounts for the thermal mass of the zone. These 2 modeling approaches, the steady state and the transient, require measurements of zone air temperature, discharge air temperature, modulating valve state, X1 to X7 here, discharge air flow rate, and occupancy indicator. Now the third modeling approach is the load disaggregation modeling approach. Hot water is provided by a steam hot water heat exchanger that distributes hot water to the radiant heaters in the 7 zones. The total hot water load measured at the outlet of the heat exchanger is disaggregated across the 7 radiant heaters by utilizing the modulating valve analog signal X1 to X7 that control the amount of hot water flow rate into the radiant heaters. Now, the virtual meter results corresponding to the 3 modeling approaches are compared with measured heat collected from physical meters installed at zone 1 to 7. As shown in this table, the 3 modeling methods could estimate the daily heat added by radiant heaters at an average normalized RMSE between 13 and 23%. These results indicate better performance for the transient and the load disaggregation modeling approach as compared to the steady-state modeling approach. Now this graph compares the predicted heat supplied by radiant heater with measured heat at zones 1 to 7 for the 3 modeling approaches. The total predicted heat for the 7 zones when applying the steady-state modeling method is around 43% of the total measured heat. This declined accuracy for the steady-state modeling approach is believed to be related to the steady-state model structure and modeling assumption, which assumes that the zone air temperature does not change over time. However, by checking the zone air temperature behavior as shown here, it is noticed that the zone air temperature starts to decline when the VAV system shuts down and rises again upon the startup of the VAV system. During these periods, the zone shows a dynamic behavior that is not captured by the steady-state model. When data points corresponding to these periods are used as model inputs, the accuracy of the virtual meter declines. Now, a simplified visualization of the results can be used as a tool by building operators and facility managers to identify zones of high energy consumption and improve the overall building energy performance. For example, this figure shows a graphical representation of the estimated heat supplied by radiant heaters at zone 1 to zone 7. By comparing the heat added by radiant heaters in the 7 zones, the building operator can identify zones of high energy consumption and investigate the underlying operational conditions of these zones. In conclusion, the 3 inverse modeling approaches were used to create virtual meters to estimate the heat added by zone level perimeter heaters. The models were trained using data collected from 7 zones, and model parameters were identified using the genetic algorithm. The results were compared to heat measurements collected from physical meters, and the accuracy of the three modeling approaches was between 13% and 23%, and the performance of the three modeling approaches was examined for modeling assumptions and prediction accuracy. Finally, the following issues are still unresolved. First, the steady-state and transient modeling approaches require discharge air temperature measurement. The models need to be modified for buildings that do not measure the discharge air temperature. Second, the number of zones could impact the accuracy of the virtual meters. Future research is planned to check the impact of increasing number of zones on the accuracy of the virtual meters. And finally, visualization tools need to be developed to present the results to different building stakeholders to support operational decisions. Thank you everybody for watching this presentation. I will be glad to answer your questions during our live session on November 18th. Thank you.